Hello friends, I Professor Darshan Thakur from Terna Engineering College Dharashiv welcomes you on my YouTube channel for this subject head Control System Engineering. As far as our today's session is concerned, so our objective is to determine the overall transfer function of that given electrical system. So friends, this is how the electrical system will look like. So in this electrical system we used to have certain basic electrical components like resistor, inductor and capacitor. So first of all, quickly we need to recall the basic definition of this transfer function in terms of control system engineering. So transfer function is nothing but what? It is the ratio of output to the input of that system in terms of S domain under zero initial condition, when none of the energy component is being given to any of that element which is present in that circuitry, right? So here the given transfer function which we want to tabulate is nothing but what? Transfer function is nothing but I2 of S upon V of S, right? So by taking into account this fact, first of all we need to analyze the given electrical circuit in terms of this Kirchhoff voltage law, right? Because as you can see in this given electrical circuit, there are two identical loops or two closed paths for that circulating current will be there. This will be the first loop and this will be the second loop. So first of all we need to assume the direction of loop currents or the direction of branch currents belongs to these two loops, right? So this will be the direction of first branch current, whose name is nothing but what? I1, or more prominently we can call it as a suffix I1 of t, and the current which is present within that second loop, that can be called it as a I2 of t. This entire circuit is to be excited with the help of this voltage denoted by V of t, and this is the polarity of this applied voltage. So as we know, always current flows opposite to the flow of electrons, means obviously it flows from positive to negative terminal. Accordingly, these two current directions are to be marked. Then after that, in order to determine its transfer function, we need to recall this Kirchhoff voltage law terminology, right? So according to this Kirchhoff voltage law terminology, we say that the summation of ohmic drop belongs to each and every element are equated to 0, right? So we need to apply this Kirchhoff voltage law to the input loop. We need to apply this Kirchhoff voltage law to the first loop as well as second loop, right? As far as the output is concerned, so the output is being taken across this capacitor. Here we are getting this output voltage denoted by V naught of t, right? So one by one we will try to apply this Kirchhoff voltage law to the first loop as well as to the second loop. So let us quickly go through. When we apply this Kirchhoff voltage law to the first loop, so in that first loop, first of all we need to map which fundamental current flows in that first loop, right? So obviously this I1 flows in that first loop. After that immediately we need to map how many relevant components we used to have in that first loop. So in that first loop we used to have one resistor and one inductor. So through this resistor purely this I1 current flows, but as far as this inductor is concerned, as it is connected in vertical arm, right? So through this inductor there will be a circulation of I1 as well as there will be a circulation of I2. But when we apply this Kirchhoff voltage law to the first loop, at that time definitely the significance of I1 is greater than I2. When we apply this Kirchhoff voltage law, at that time I1 is greater than I2, and when we apply this Kirchhoff voltage law in that second loop, so at that time I2 is greater than I1. That such type of hypothetical assumption we need to do. So by taking into account this fact, see, this is the positive plate and this is the negative plate. When we apply the Kirchhoff voltage law to the first loop, at that time, as we are going from negative plate to the positive plate, due to this its potential will become what? Plus V, or that can be rewritten as a V of t, right? V of t. Then immediately after that, which component we are having in that circuitry? We are having this resistor R1 and this inductor L. So immediately after that we need to map how this branch current I1 flows through this resistor R as well as this inductor L, right? So this R is connected in horizontal arm. So obviously there will be a circulation of current from this left hand side to the right hand side. So these are the polarities. How this I1 flow through this inductor from top to bottom. At the same time, because through this inductor there will be a circulation of I1 as well as I2. So what will be the direction of I2 from bottom to top? Like this, right? So according to this, as we are going from positive to the negative polarity of this resistor R, so according to that Ohm's law, voltage drop across that resistor will be what? V equals to I into R. So which current flow through this R1? I1. So it will become I1 of T into R1. Similarly, the ohmic drop across that inductor, how the ohmic drop across that inductor is to be denoted? VL equals to L di by dt, right? With this expression, the ohmic drop across that inductor is to be denoted. Similarly, the ohmic drop across that capacitor will be 1 over C integral of I of t into dt, in this way, right? So the ohmic drop across this inductor, or the polarity of this ohmic drop will be what? As we are going from positive to the negative plate, so obviously it will become what? Again negative. So minus of L, which current flow through that inductor? I1 as well as I2. But when we are in first loop, so at that time I1 is greater than I2. So by taking into account this fact, this statement will become what here? D by dt followed by I1 of t minus I2 of t. I will put this entire term within this square bracket, like this, right? So our resultant statement for this input voltage will become what here? It is Vi of t equals to I1 of t into R1 plus L d by dt followed by I1 of t minus I2 of t, right? As we know, transfer function is nothing but what? It is the ratio of output to the input in terms of S domain. So in order to convert this time domain expression into the S domain expression, we need to apply the Laplace transform to this existing statement. So as a result of this, it will become what? The Laplace variable will be S, I1 of S followed by R1 plus. Here as we are having the differentiation operator, it is the first order differentiation. So the Laplace variable will be S. So Ls into I1 of S minus I2 of S, right? This is nothing but what? Equation number 1, right? Now in same manner we need to apply this Kirchhoff voltage law from this output side, or we need to apply this Kirchhoff voltage law into the loop number 2 or the mesh number 2. So first of all we need to map how many components we used to have in that loop number 2. So within this loop number 2 there are 3 identical components. Those are nothing but L, R2 and this capacitor C. There are 2 energy storing elements, one is inductor, one is capacitor and one resistor. Now which current flow through this capacitor C, that we need to understand. So this purely this I2 flow through this capacitor C. Similarly, there will be a circulation of this I2 through this R2, because these two components are connected in series form, right? But as far as this inductor is concerned, as I told you earlier, it is connected in vertical arm, so there will be a circulation of I1 plus I1 as well as I2, right? But when we are in second loop, so at that time the significance of I2 is greater than I1, right? So when we apply this Kirchhoff voltage law to the loop number 2, at that time, this is according to this Kirchhoff voltage law, the summation of all ohmic drop are equated to 0. So we need to find the ohmic drop across this capacitor, this resistor R2, and the ohmic drop across this inductor L, right? So we will start our journey with this capacitor C. So the ohmic drop across that capacitor, which relevant statement we need to use? It is 1 over C integral of I of t into dt. So which current flow through this capacitor C? I2 flow through this capacitor. I2 current flow through this capacitor C. So the statement will become what here? Here I will write that KVL to loop number 2. As a result of this, it will become, or when we write this KVL equation is in terms of this output voltage, or from that output side when we apply this Kirchhoff voltage law, so it will become V naught of T, right? Because this is positive plate and this is negative plate, right? So V naught of T equals to the ohmic drop across resistor, capacitor and inductor. So the ohmic drop across this capacitor will be what? 1 over C integral of I of t into dt according to its basic definition, plus the voltage drop across this resistor R2 will be what? V equals to I into R. So R2 into I2 of t, right? Plus, as far as this inductor is concerned, so the ohmic drop across this inductor will be what? L into di by dt. But as far as this I is concerned, so which current flow through this inductor? I2 and I1, and their directions are opposite to each other. That's why we need to consider the negative sign, just similar to the way in which we had applied the Kirchhoff voltage law to the loop number 1. So it will become what? Plus L into d by dt followed by I2 of t minus I1 of t. This is nothing but what? The time domain expression. And when we apply the Laplace transform to this existing statement, so this whole statement that can be rewritten as a, here I will write V0 of S equals to, it is 1 over C when we are having the integral sign, so which Laplace variable we need to consider? 1 over S. So the statement will become what here? 1 over Cs into which current flow through this capacitor? I2 of S, right? Plus R2 into I2 of S, plus the ohmic drop across this inductor, how it is to be written? L d by dt followed by I2 of t minus I1 of t. When we apply the Laplace transform to this statement, so as we are having the first order differentiation, so which Laplace variable we need to consider? S. So Ls times of the statement will become what here? I2 of S minus I1 of S. This is nothing but what? Our equation number 2. So in that first step, we need to obtain these two system equations by applying Kirchhoff voltage law to the input side, or as well as to the output side, or to loop number 1 as well as loop number 2. Then after that, what we need to do, our aim is to determine the transfer function, that is nothing but what? The ratio of I2 by S upon V of S, or Vi of S, right? So after that, immediately we need to simplify these two existing equations to determine its overall transfer function. Okay friends, so once we had applied the Kirchhoff voltage law from this input side as well as from this output side, so we are having these two identical equations which we had derived by applying Kirchhoff voltage law, right? Then after that, what we need to do, equation number 1 represents the loop number 1 or the input side, equation number 2 represents the loop number 2 or the way in which we had applied the Kirchhoff voltage law from that output side. Its system equation will be what? V of S equals to 1 over Cs times of I2 of S plus the ohmic drop across this resistor R2 into I2 of S plus the ohmic drop across this inductor. When we apply the Laplace transform, so it will become Ls times of I2 of S minus I1 of S, because their directions are opposite to each other, and in that second loop the I2 is greater than I1. Then after that, simply few mathematical simplifications we need to do to determine this overall transfer function. So let us quickly go through this mathematical simplification. In that next step, what we need to do, as far as this last term is concerned, that is nothing but what? Ls times of I2 of S minus I1 of S, right? Here we want this term in terms of Ls into I1 of S minus I2 of S. So for that purpose, intentionally, your negative sign can be considered as a common term. So as a result of this, it will become Ls minus of Ls into I1 of S minus I2 of S. Then after that, this whole term is being shifted to the right hand side of this assignment operator. As a result of shifting, it will become V0 of S plus Ls into I1 of S minus I2 of S. The remaining term which is present to the right hand side of this assignment operator will be 1 over Cs into I2 of S plus R2 I2 of S. Then in that next step, what we need to do, this V0 is being shifted to the right hand side, because which term we want? We want this entire term, that is nothing but what? Ls times of I1 of S minus I2 of S, because this term is indicated in this equation number 1. So we want the desired system equation in terms of Ls into I1 of S minus I2 of S. So we can replace that value in that equation number 1. So for that purpose, specifically or intentionally, this V of S is being shifted to the right hand side of this assignment operator. As a result of this, it will become minus V0. So here, instead of minus V0, we need to write minus V0 of S plus remaining term as it is, right? Then after that, to that both side, we need to consider the significance of this LCM, that is nothing but what? CS. So it will get cross multiplied with each and every term. But before that, what we need to do? We need to replace this term Ls times of I1 of S minus I2 of S. This entire value is to be substituted in that equation number 1. Means this whole term is being represented with this remaining term minus V0 of S plus 1 over Cs times of I2 of S plus R2 into I2 of S. So as a result of doing this, the equation number 1 will become what here? V of S equals to R1 I1 of S, as it is, right? Then this whole term is being replaced with this alternating quantity, that is nothing but what? Minus V0 plus 1 over Cs I2 of S plus R2 into I2 of S. Then furtherly, this Cs can be considered as a LCM term to the right hand side as well as left hand side. So as a result of this cross multiplication we need to do. So V of S is being multiplied with this Cs. So it will become V of S into Cs R1 I1 of S into Cs minus V0 times of Cs plus 1. Then after that, here these two terms are sharing the similar coefficient, that is nothing but what? I2. So that can be considered as a common term. So the remaining terms are 1 plus R2. So in this way we are getting this system equation, and this system equation is to be rewrite is in terms of I2. So it will become what? I2 of S equals to, the numerator will become what? The total term which is returned to the left hand side of this assignment operator. So it will become V of S, here I will write V of S into Cs minus R1 Cs into I1 of S, right? R1 Cs into I1 of S minus V0 times of Cs. This whole term divided by the coefficient of this I2 is nothing but what? 1 plus R. So this is the desired term of this I2 of S, which is indicated in this numerator position. Then after that, what we need to do as far as this denominator is concerned? So denominator is nothing but what? This equation number 1. This whole equation is to be we need to write within the denominator place. So it will become what? This whole system equation is to be replaced within this denominator, and that will be our desired transfer function equation. So in this way, the overall transfer function of this electrical network is to be tabulated by the virtue of Kirchhoff voltage law. Thank you.